In this module, we're going to look at doing routine maintenance on databases. We're going to start off by first looking at how to ensure database has integrity by using the DBCC commands. Then you're going to look at how to maintain indexes using the DBCC commands. And we're going to talk the difference between reorganizing and rebuilding indexes and why indexes have to be maintained. And then we're going to finish up by looking at how to automate routine maintenance using database maintenance plans. So now we're going to talk about how to verify the integrity of our databases, as well as how to do some repair when there are integrity problems. Now, it's kind of important to note here, when we're talking about integrity here, we're talking about integrity in storage. We're not really talking about integrity through the use of constraints that developers will create so that if you put a record in one table, that there's a corresponding record in another table. That's not what this is. What we're looking at here is first we look at physical integrity, and that is making sure that the data is stored in the files that it claims to be stored in that have been allocated through our database creation and through the altering of our databases, and to make sure that SQL can actually read that data from those files. More importantly for us, when we talk about logical integrity, when we start to create objects and we start to store things, remember we talked about this previously, you have pages, and pages are 8K in size, and so they store data for a table, and then that information gets put into extents. There are 8 pages to an extent, so that's going to create a 64K storage block, and then that information is then stored, again, depending on whether I have mixed extents or single-use extents, that information is going to get stored in the database files. When SQL goes to retrieve that data, in order for it to be able to retrieve data in an efficient manner, it has to know that when I'm looking for row so-and-so, that it's on page Y. And that information is what's used with the logical integrity. So we have tools to make sure that that integrity is maintained and that SQL believes the SQL data is actually where SQL believes it is. So when we look at the tool that we have for doing logical and physical consistency checks in our database, it starts with DBCC. Now, the text is going to tell you that DBCC used to be called Database Consistency Checker, and now they call it Database Console Commands, to indicate that it's more than just checking the consistency of a database. It's doing a lot of other options. The CHECKDB option checks for the physical and logical integrity or consistency within the database. It checks to make sure the database is correctly stored. It checks the tables to make sure that they're correctly allocated and pointed to logically within the data. And it also checks the system catalog to make sure that all of the system objects are properly referenced and the metadata points to the correct information. These are all part of the CHECKDB. You can run these separately. So you can run DBCC check table, DBCC check allocation, check alloc, DBCC check catalog by themselves to check those components specifically. With DBCC, if it finds problems, it gives you the ability to do some repairing. Now you're going to see in a demonstration a little bit later on how this can be a dangerous operation. When you run the DBCC, we have the ability to control what type of output we get from it. And when that output comes out, it'll tell us whether we can do repair or not, and whether we can do repair with data loss or repair without data loss. If we do repair with data loss, it's going to fix the consistency problems in the allocation, the logical consistency, but that's going to remove rows potentially from the data, which could cause problems in consistency of the data. And you're going to see this a little bit later on. As a general rule, you would try to avoid doing the DBCC repair options and rely on restore options from database that's been backed up from a consistent state. That being said, one of the things that we use DBCC CHECKDB for is before we back up a database as part of a maintenance plan, we'll run CHECKDB to make sure that the database is in a consistent state before we back it up. It's almost like saying the data is in a good known state here, before we back it up, so it's a good clean backup. When it runs, it does internal snapshots of the database, and that takes up space in TempDB. There is an option to run the estimate only parameter to determine how much space it's going to consume in the TempDB. You can look at that to determine if maybe you want to run this at a different time. You can also force it to grab table locks instead, which will consume less disk space, but it's going to have more of an impact on the users that are attempting to use the objects that are being referenced by the DBCC command. And as they mentioned here, you should run this fairly frequently as part of your backup strategy to make sure that you're backing up good data. There's no point in doing backups and not knowing whether the database is good or not, and then having to do a restore, and then you keep having to restore backwards and backwards until you find a consistent state of the data, which means you lose everything between that time point and where you found the problem in the data set to begin with. If you have created file groups for a database, you can actually use DBCC to only run the checks against specific file groups instead of running the check against the entire database. And similar to what we mentioned earlier, one of the big advantages of file groups is for maintenance. This is one of those examples where it only affects the objects that are part of that file group instead of affecting all of the tables in the database. So some of the options that we have when we're doing the DBCC CHECKDB, these are parameters or options if you want to call them that. We can tell it to only do the physical checks, so not do any of the logical checks to check to make sure that rows are pointed to correctly by things like indexes, or rows are pointed to correctly if we have heaps where we don't have a clustered index created. This will be a lot less overhead. However, it means that the data may not be logically pointed to, and that could be a big issue. We can tell don't do the checks on indexes. Generally, we would do this if we're going to do a rebuild of the index anyway, or we're going to reorganize the index, usually a rebuild. We can tell to do extended checks. By default, the DBCC CHECKDB does not check certain types of objects. And the list here, indexed views, so if I create a view with an index on it, it does not do it for spatial data, points to longitude, latitude numbers. It does not do it on XML indexes. So we could tell it to go ahead and do it on those types of objects as well. It would depend on what type of data is in the database as to whether I would do the extended logical checks or not. We can tell it to grab a table lock instead of doing a database snapshot. This is going to reduce the amount of space that's required to do the CHECKDB, but it's going to involve more potential issues with users accessing the data that's being checked for physical and logical consistency. You have to weigh the advantage, disadvantage with the amount of space that's going to be consumed in the TempDB versus the amount of impact it's going to have on live operations in the environment. Then we have the ability to control how much feedback we get. Now, we can tell it to do all messages, and that is the default operation, so it's going to return everything. I'm sorry, instead of just the first 200 messages. Now, it's going to return all messages, informational and error, but it's only going to return up to 200. Now, keep in mind, when we talk about informational messages, we're going to get an informational message for every object that it does the check on. So every table in the database is going to give me a row of an information that it checked that table. So keep that in mind. We do this so we can see all the output. As a general rule, we don't run the all error messages. We just want to tell if there's actually serious problems. So we normally say no info messages, where it only tells us if there are problems and only if there are error conditions. The caution here is that if everything works correctly, like many other types of commands, all you're going to see is the command completed successfully, and you're not going to really see any output from it. So you have to weigh that with what you're trying to accomplish. Now, if you're doing this as part of a maintenance plan or part of a scheduled operation, you probably don't want much feedback anyway because you're not looking at the screen that's going to be producing the output. you're going to be dumping it to a log file that you'll come and view a little bit later on. As I mentioned earlier, we can tell the estimate only option to tell us how much space would be needed in the TempDB. It doesn't actually run the CHECKDB, it doesn't actually start the snapshot. It just tells us how much space will be required in the TempDB to create the snapshot of the database. So when we run the CHECKDB and we see that there are problems, we can try to do some repair on the database. And the output of the CHECKDB command will tell us what level of corruption it has found and what type of repair it thinks we can do on the database. So as you can see here, in order for this to work, the database has to be in single user mode. Remember, if I use Transact SQL to set it in single user mode, I have to stay inside that same connection in order to try to do the repair, because I've already got that one connection to the database and nobody else is allowed to connect to the database. It's also important to note if I've already opened one query and connected to the database to run the DBCC CHECKDB, and then I open another query window and I attempt to run set the database into single user mode, that's going to fail because the database is already in use. All right, so you've got to close one of those query windows. When we run the DBCC CHECKDB, the two options that we have are we can do repair, rebuild, in which case it's going to try to repair the database, the logical, physical consistency without losing any data. The output will tell us if we can do that. If not, we'll have to say repair, allow data loss. And under most circumstances, this is almost never a good plan. You're better off attempting to do a restore of the database if you have a backup. Now, unfortunately, if you don't have a backup of the database, or the backup of the database is so old, it's not going to work very well. What you probably should do at this point is back up the database that you have now. Yes, it is corrupt, we know that, but at least we can try to use some of the data from that later on when we're trying to piece the data back together. Then you would run the repair, allow data loss. You're going to see this in a demonstration, and you're going to see how bad this can really make things. They've purposely created some corruption in some tables, and you're going to see where we have an orders table and an order details table, and we have corruption. And when we do the repair, allow data loss, it ends up fixing the problem to allow the data to work, but it fixed it by deleting a page that had a bunch of rows in the order details table. So now I have a bunch of orders that don't have any details about what the order is. So I really don't know what the order is about. So again, instead of doing repair, allow data loss, your better option is to do restore the database. They also mention in the text that you can actually try to force start a database that won't start because of corruption. But again, almost always that's going to involve problems that you're not going to be able to fix easily unless you know all of the data and you have another source for that data would be the best way to do that. So you can see in this example here that what we have is right down in here we have the CHECKDB running, and it tells you that it found 4 errors and that the minimum repair level is allow data loss right there. So generally when you see this type of output, you're better off trying to do a restore. Now you'll notice that they did CHECKDB for the AdventureWorks database, and they said with all messages. So again, this would return over the 200 messages that we would normally have a limit on when we ran this command. In this demonstration, we're going to see how to use the DBCC CHECKDB command. In this demonstration, we're going to look at how to use the DBCC CHECKDB SQL Server command. Now we're going to look at a couple options with this. First, we're going to run it with no options, so what they call the default options. And then we're going to look at some of the different options that we have. So with no informational messages, they've created some corruption in a database, and so we're going to see some of the errors there. So first, let's run it against the AdventureWorks database. So we run this, and you can see it's going to check the AdventureWorks database for potential issues. And notice that there are 2,000 rows for the object, and you can scroll through the output from this, and you can see that if there are any problems, it will indicate to you where these problems might exist. And even in some cases, if there are serious problems, specifically which page is damaged, and we're going to see that coming up in the corrupt DB. So here we're going to tell it to just run it with no informational messages and only tell us if there's any problems or errors or potential corruption issues in the database. And this database is perfectly fine. There are no issues with it. So now we're going to run the same command against the corrupt database that they've created for the class. And what you're going to notice is we're going to have some errors that indicate there's some problems. So see this right here? It's telling you that in the index ID, in this allocation unit, we have some problems, some corruption. And notice right there, the page number. That page number is going to become important later, and you can see a couple of different page numbers, because when we go to do repairs, if we were going to do a restore operation, try to fix this problem, we could restore just the page that's damaged. We're going to talk about restores later on. For right now, we're just looking at the DBCC command. So what we're going to try to do is, since we see that there are problems, we're going to try to grab data from this database. And because the database has corruption, you can see right there, logical consistency-based I/O errors, checksum problems, it's not allowing us to access the database. Now, instead, we could access specific rows that are not on the pages that are corrupted, so it allows us to access certain data. And this is the issue that you're going to have when you have corruption in a database, when you have some potential problems with the storage units or the storage allocations where the database is stored. So what we're going to do is we're going to run alter database on this database, and we're going to set it in single user mode so nobody else can be in the database while we're fixing it. And we're going to run the CHECKDB command with the corrupt DB as the database, but we're going to do it a repair and allow data loss. And what you're going to see is this can actually cause some consistency problems in your database. So we're going to run this all together. So we're going to set it first in single user mode, then we're going to turn it back into multi-user mode after we run CHECKDB, do a repair, and allow data loss. So once that is complete, you're going to see that it actually went through, and this is the, remember with the DBCC with no options, it shows us informational messages. And if we go all the way to the bottom, we no longer have, there's the error messages that we had originally, and you see it's been repaired, right? So this is what it did with the repair allow data loss. So now when we try to access all of the rows in the table, it works fine, but here's where the problem is going to come in. This table, orders, has a foreign key constraint to data in the order details table. So first we're going to run the CHECKDB with no informational messages, and everything's going to work fine because we no longer have any errors in the database. However, when we go to make a selection from the two databases where they have rows in common, watch what's going to happen here. So see this right here? We have where it doesn't exist. So these are rows in the order details table that we don't have corresponding orders for in the orders table. So you can see there are 42 rows that got removed from the orders table, and now we have a consistency problem in our database. And this is where you would think about doing a restore based on the damaged pages maybe, or even just based on certain data back to a specific point in time. This is the caution you have to be careful of using the CHECKDB repair allow data loss.
In this demonstration, we got to see how to use the DBCC CHECKDB command, as well as how to implement the DBCC CHECKDB parameters, including recover with data loss, and to view how that data loss affects the environment. So one of the best tools that we have for improving performance on SQL data is indexes. Now, there are two types of indexes we have. We have clustered indexes, we have non-clustered indexes. Clustered index is created based on the way the data is going to be initially stored in the object, so in the table, based on key columns that we're going to use. Non-clustered indexes are going to have pointers back to the data of where it physically resides in the SQL Server structure. Now, to get a better concept of this or better grasp, clustered indexes would be like the table of contents in a book.
You can look at the table of contents to tell you exactly what page that's on. A non-clustered index is like the index in the back of a book with pointers to the different locations of where that data is stored. So if I don't have an index on a table, what happens is SQL Server is going to have to scan all of the data from all of the pages to find the necessary rows that are going to be required to return the data for the query and bring that data into the data cache in the buffer pool. So again, remember, it's always done based on a page, so it's going to find the appropriate page and bring that page in. If I have an index, the index has a root level that identifies the different non-leaf level pages that are actually going to specify, again, in further storage locations. So think of this: if you ever go into a library and you walk into the library and you walk down the rows, every bookshelf has a range on it, and then once you go down the range, you then have each shelf has a specific range of books that are on that particular shelf. So this would be similar. This would be like the card catalog that would tell you how to find the information. This would be like the shelf, like the row of the bookshelves. And then I'd have another one of those that would actually be the row of the books. And then on that row, I would be able to find the individual book that I'm looking for. That's what an index helps me find. And so SQL can search just here, here, and then find that without having to look at every single record that's in every single page to find what it needs. This information is covered in great detail in the developing SQL databases because it's a big part of identifying what indexes work based on what type of data you have, based on the uniqueness, based on how the data is going to be used. That's where the indexes come into play. The reason we cover it here is because when we start to create indexes, part of our job as administrators is going to be to maintain these indexes, especially as data changes in the tables, to make sure the indexes are still relevant and that they're up to date and that SQL knows that they're up to date and uses the appropriate index to retrieve the appropriate data. So as mentioned previously, there are two types of indexes. The clustered index has data pages in the leaf level. So down at the bottom you have data pages down in the leaf level environment. So these are going to be your data pages. And they're going to have specific rows based on a specific range. Non-clustered indexes are going to have pointers to those rows down in the leaf level. So what we're going to have is pointers that are going to identify back to where the data is stored in the data pages if there's a clustered index. If there's no clustered index, the non-clustered index is going to point to the heap where the data is stored down below. Now, you'll notice here you have the root node that we talked about in the previous slide, and then we have the intermediate level nodes. There can be multiple levels of the intermediate level nodes, and this is going to be important later when we go to set up properties, when we build an index on things like the fill factor and the pad index, on whether we're going to leave space for new changes at just the leaf level pages or whether we're going to leave some space also in the intermediate level pages, which is going to be what's called the pad index. So as mentioned previously, SQL creates a bunch of objects that allow us to get information about the environment, and they're referred to as dynamic management objects. Dynamic management views, DMVs, and dynamic management functions, DMFs. Now you don't normally see the V or the F, but they're different types of components. What they allow us to do is retrieve information that's maintained by SQL. You'll notice in this example here that all of them always are from the SYS schema. So they're part of the SYS. Remember, the SYS schema is part of the resource database that we talked about previously. There's several different categories that these things are associated into, and that allows us to identify the particular information that's being retrieved. There's categories for server services, there's categories for databases, there's categories for security, there's categories for transactions, and there's categories for indexes. So you can see some of these have the information, and you can see right here we're getting this from the dynamic management. Technically these are views here. we're getting information about the DB index usage stats. So just statistics about the usage of our indexes. One of the things to keep in mind with indexes, and again, covered more in the developing class, but when you build an index, it has to be maintained and it has to be stored somewhere. So this is going to be overhead. So you might have indexes you don't need, and therefore you're consuming space, and these things have to be maintained. So this will tell us which indexes are being used and the frequency with which that's being used. We have index operational stats, so how the index is being used, how many seeks have been run against the index. We have the physical stats of the index, which is going to tell us about the physical configuration of the index, its size, its fragmentation information. We can also see missing index details. So how many times SQL Server had to do a table scan as opposed to using an index to access data within an environment. All of these things can help us identify when we want to use indexes and which indexes are needed and which indexes are not. It's also important to note that the SQL Server Profiler can be used to capture workloads. We can use that with the index tuning wizard to identify missing indexes as well. So fragmentation is a function that occurs with indexes, usually when data modifications occur in the tables. Indexes are always associated with tables or views. And when we create the index, what's going to happen here is as we add data to the table, if there's no room for the row on the index page, then it's got to do what's called a page split, where it's got to take one row from that page and move it to the next row to create space where the row belongs. When that happens, more commonly than not, it's also going to have to do a split on the other page, and then a split on the page after that, and so on, until it gets to the last page of the index. And that's an expensive operation. So what we can do is just put the row at the end of the index, and that's going to cause what they call external fragmentation, because now the data is not in the logical sequence. So now what SQL has to do to find the row is it's got to look at the logical location and then look at the back of the index to see if there's any rows out at the back that have been externally fragmented. Internal fragmentation is when not all of the pages are full, and that's actually by design, not by accident. However, it means that the storage space is going to be larger to hold the index. So you got to be careful. It's a balancing act between leaving enough space in the pages to add new rows and making sure that the index is the right size. We can control that through a process called the fill factor when we create and rebuild our indexes. You can detect this fragmentation by looking at the properties in the SQL Server Management Studio. You can right-click on the index and click on properties, and it'll tell you what both the internal and external fragmentation are. And we can also use the index physical stats database management view that we talked about in the previous slide to identify it. As a general rule, we're looking for about 30%. If we have an index that's more than 30% fragmented, we're probably going to want to rebuild that index. If an index is less than 30% fragmented, we're going to want to do a reorganization of that index. A rebuild takes a lot more time, and generally when we rebuild an index, we drop the existing index and recreate it from scratch. So when you're building an index or rebuilding an index, you can leave empty space in the index pages to allow new rows or modified rows to be put into the correct space or the correct order where they belong. We do that by specifying a fill factor. Now the fill factor is a percentage of the amount of space that the page will be used initially. Keep in mind that it's not maintained at that level, it's just when the index is created or rebuilt that it uses the fill factor value. So in this example here, the fill factor 70 means that this index will be filled, every page will be filled at 70%. And notice the pad index is off, so it means it's only going to do it for the leaf level pages. So only at the very bottom will it actually use the 70%. The non-leaf level pages, the intermediate pages, and the root pages will be filled completely when they are created. When we set the fill factor up, we're creating, on purpose, internal fragmentation. So we have pages that are not filled, but we're doing that on purpose so that we can allow the data to be modified and still be maintained in the correct order. So as mentioned earlier, indexes require maintenance because the data in the underlying tables that the index is built on changes. So over time, eventually there's no room left to put in rows where they belong, so either it externally fragments or it does a series of page splits to try to put the row where it belongs in the clustered index. When we do maintenance of indexes, we have two options. We can rebuild the index or we can reorganize the index. And as mentioned previously, reorganization sorts the pages and doesn't really move a whole lot of data around and doesn't take up a whole lot of transaction log space to do the reorganization. When it does the reorganization, it's going to use whatever the fill factor was that was defined when the index was built. It can be interrupted because it's not actually recreating the index, it's simply moving data around. So we can actually interrupt this and pick up where we left off later on. And that's one of the big advantages of a reorg. The problem with a reorg is if the index is more than 30% externally fragmented, it most likely is going to require you to do a rebuild because the overhead of doing the reorganization and moving everything around is usually too costly to the SQL Server. To do a reorg, you alter index on the name of the index or all, on whatever table that we're talking about, and then we say reorganize. If the index is more than 30% externally fragmented, we're going to want to do a rebuild. A rebuild is going to need a lot of free space to do that because it's going to actually create another copy of the index and move the data over to the new copy that's being created. It's going to be done as a single transaction, so we can't interrupt this and come back to it later on. And it requires a large amount of space in the transaction log because it's going to record the movement of the data that's being altered. Remember that a clustered index is how the data is actually stored in a table, so we actually have to move things around in the actual storage of the table in order to build the clustered index. To do the rebuild, we can say alter index, the name of the index. Notice you generally don't say all, so this is a specific index. You'll notice here the CL right there, which is for the clustered index. This is the table that the index is on, and this is the rebuild option. There's also an option you'll see oftentimes with drop existing. And what that will do is rebuild the index by dropping the current index instead of trying to copy it over into the free space of the database and resorting. Now we're still going to need lots of log space even when we do drop existing, but we don't need as much space in the database to recreate the index. So when we do reorganizes of index, they're always done as an online operation, which allows access to the data while the index reorganization is taking place. But if we do a rebuild operation, or we do a rebuild with drop existing, or we're creating a new index on a table, a clustered index specifically, it allows access to the data if we specify the online option. In order to make sure that things aren't changing while we're moving them around, it does these short-term share locks. Share locks are compatible with other share locks, which means that we're reading the data. Somebody else can read the data at the same time, but they can't change it while we're actually doing the movement of the data. It's also important to note that when we do this online operation, it's going to do these things called schema locks, and that prevents any structural changes to the underlying tables. You can't create the tables, you can't modify the table, you can't drop the table while the index operation is taking place if it's done as an online operation. Also notice what happens here is this is going to be a lot slower than the offline operation because of the locking contention and the contention of the data that's going on while the index rebuild is taking place. So in this example, we're going to alter the IX index in the contact email address, that's the name of the index. On the person contact table, we're going to do the rebuild. We're not going to do the pad index, so we're only going to do the leaf pages, not the root pages or the intermediate pages. We're going to fill the pages to 80% of capacity. We're going to do this as an online operation and use up to 4 processors for the operation in parallel. So while data changes in a table, SQL Server uses information about the indexes it's used previously to build its query plans to identify the best way to access data in the tables. Now, we already talked about the update stats option, especially when we're talking about migrating data. When we do the attach database, they tell you to update the stats at the end of that so that SQL knows about the data that's present. These are options that we can enable on a database. So we can enable the auto create stats and the auto update stats so it automatically rebuilds the statistics when the underlying data starts to change. We can also manually force the update of statistics in a query as part of a query. We can do this on demand for a specific table by saying update statistics, the name of the table. We can also run a stored procedure, SP update stats, that will update all of the stats for a specific database. So at the end of the update stats space, we will put in the name of the database and it'll update the statistics for all of the tables in that particular database. Now again, we do this so that we can try to make sure that the query optimizer is going to make the best decisions for the query plan when it's trying to access the data. In this demonstration, we're going to look at the process for maintaining indexes.
In this demonstration, we're going to look at how to maintain indexes by rebuilding the index. So first we're going to create a table. We're going to put some data in the table. And that's what this is doing here. So first in the AdventureWorks database, we're going to go ahead and create a table. And then in that table, we're going to add a series of rows. So we're going to add 10,000 rows into this table. And then we're going to check for the fragmentation once the row insert has completed. So the row insert is completed, and this command here is going to check for the fragmentation. Notice we're using dynamic management view for physical stats, and we're grabbing on the database ID, and the ID that we're looking at here is the phone log. And if you come back up here, that's the name of the table that we created. So we're looking at the detailed fragmentation on the phone log table. So if we scroll out, you'll see that there's a clustered index. Clustered index got created automatically when we set up the primary key constraint right there when we created the table. And if we scroll out here to the right, you'll see the average fragmentation in percent is about 1%. So it's really not bad at all. Now what we're going to do is we're going to modify a bunch of data in the table, and that's going to cause some fragmentation in the index. So right here we're going to modify data in the table. And this is going through and modifying every row in the table. So see the counter is going to 10,000, the same number of rows that we had in the table. And now we're going to check that fragmentation again on the phone log. And this time when we scroll out, look at the average fragmentation now. It's 90%. So now we have a lot of fragmentation in the table, a lot of fragmentation in the database based on the index, a lot of fragmentation on the index itself. So now what we're going to do is we're going to alter the index, DBO phone log, and we're going to rebuild it. And we're actually going to alter all of the indexes that we have. All right, so it's actually going to rebuild all of the indexes on the phone log database. I'm sorry, the phone log table in the AdventureWorks database. So right here we're going to go ahead and we're going to alter the index and do a rebuild of the index. Now that was very quick because there's not a whole lot of data in the table and there's only one column on the index. Just keep in mind in production environments that can take considerably longer to do that rebuild. So we run execute, and if we scroll back out, the average fragmentation in percent is now 0. So that is one of the things that you'll need to do on a lot of databases as part of the maintenance. It's a property of the database maintenance plans when you create database maintenance plans on databases that you can have it automatically rebuild your indexes.
In this demonstration, you got to see how to maintain indexes. We also looked at the process for checking fragmentation, identifying the fragmented indexes, rebuilding and reorganizing indexes. So one of the ways to implement these maintenance functions for indexes and for other things within a database is to create maintenance plans. Now, maintenance plans utilize the SQL Server agent service in order to be able to schedule these maintenance plans to run. We can create them separately, but in order for them to automatically run based on a schedule, we have to have the SQL Server agent service running on our SQL Server instance. Within the maintenance plans, we can create many different built-in tasks such as checking the database integrity, DBCC CHECKDB, shrinking the database, removing unused, returning unused space back to the operating system, consolidating data within the database files, rebuilding and reorganizing indexes within the database, backing up the database, updating stats. These are all things that we can do as part of a maintenance plan. Two ways to create a maintenance plan. We can use the database maintenance plan wizard, which is a graphical tool that'll walk us through this process. We can also simply create a database maintenance plan and build a sub-plan and manually put in the tasks. It's also important to note that we can actually use the database maintenance plan and put in a query that we've written that will update certain information. So let's say that we want to reorganize certain indexes and rebuild certain indexes. Instead of manually clicking the boxes that we want, we can write a script that will do that and simply import that script when we're creating the database maintenance plan. When we create a database maintenance plan, it's going to create an SSIS package that's used to store the plan, but it doesn't store it under the SSIS node. Instead, it stores it under a node within the SQL Server agent under the database maintenance plans. We can then run that package from that location. If you remember, SSIS stands for SQL Server Integration Services, and it's basically the tool that lets us bring data in and out of a SQL environment. So after we create our database maintenance plans, if we schedule them to run on a specific schedule, we can monitor that through the job activity monitor in the SQL Server agent. They're going to run as jobs within the SQL Server agent. In addition, the results of these jobs and what's being populated inside the SQL Server agent properties is actually stored in the MSDB database. We can also, as part of a job, specify that when the job completes, or if the job succeeds, or if the job fails, to have it send information out as a text file, so we can write the results to a text file that we would then identify as a log file to speak of. We can also, assuming we've done some work and created things called operators and set up SQL mail, we can then have an operator be notified via email that this job has successfully completed, when it completed, or if it failed, what the outcome was and what job step it failed on. Those can all be identified through the SQL Server agent service, and we can then automate the process. We can also specify that this information is maintained in the database and certain information is cleaned out after so much time period has expired. If you remember in the previous slide, we talked about we can create jobs to clean up the history. Well, that's what this lets us do, to identify our retention policies for how long this information needs to be maintained inside the MSDB database. In this demonstration, we're going to look at how to implement a database maintenance plan.
In this demonstration, we're going to look at how to create a database maintenance plan. Now, in the previous demonstration, we talked a little bit about you can use a database maintenance plan to rebuild the indexes on a database, but you can use it for a lot of other things. In this demonstration, we're going to look at how to shrink a database, we're going to look at how to rebuild an index, and we're going to look at how to update stats using a database maintenance plan. There's a lot of other things we could use it for. We could use it to back up the database. We could use it to import data. So in this example, we're going to look specifically at maintaining
the database information. So first we'll come down into our maintenance plans and we will create a new maintenance plan by using the maintenance plan wizard. Now there's two different ways of doing this. The wizard will walk you through creating the appropriate steps. The database maintenance plan itself allows you to use transact SQL statements and create steps that are going to be done. Gives you a little bit more latitude, but it's a lot less intuitive. So we'll start with the database maintenance plan wizard, and you can see some of the things that we can use it to do. So we're going to start off by giving it a name, and the name that we're going to put on this is for optimizing AdventureWorks. Now again, we give it any name we want. We can also control how it runs. We can specify schedules for it within here. Then we're going to check the things that we want it to do. Now what we want it to do in this example is we want to shrink the database, we want to rebuild the index, and then we want to update the statistics. But again, notice some of the other built-in tasks that are available. DBCC CHECKDB that we did in a previous demonstration. Reorganizing indexes instead of rebuilding them. It's a little bit more efficient, but could take a lot longer to do. We can clear up the history, we can execute a job, we can back up the database, we can clean up the maintenance information that's been accumulated over time. So then we'll come into the screen where we're going to tell it how we're going to do the tasks. Now we're going to tell it what database that we want to run these tasks on. So in the drop down box we will select AdventureWorks. Now you want to be aware here, I could say all databases, and the advantage of all databases is that if I add new databases in the future, they will get this maintenance plan. If I say all user databases, any databases again that I create in the future will automatically get this plan. If I check these boxes, it's only those databases, and if I add a new database in the future, it will not get this plan. I would have to modify the database maintenance plan. So notice we're going to shrink the database when it grows beyond, in this example, 50 meg. Again, we can control the amount. So this is going to show us each of the tasks that we're doing here. And we're going to specify how much free space to allow in the database after the shrink operation is complete. Notice it returns the space to the operating system. We could also just tell it to free up space in the database files, but leave the database as using that space. Then we're going to specify the rebuild task. So again, we're going to go to our AdventureWorks database, and we're going to tell it what objects we want to rebuild. So we're going to do this for all tables and views. We could specify the free space per page that we want to allow. So we're going to talk, this is going to be allowing space to be allowed. It's called a fill factor. So allowing a fill factor. Do we allow the fill factor on the pad indexes? We can also control how it does the operation, so we can define the max degree of parallelism. We can specify that it should only rebuild the index if it's more than 30% fragmented, so we can control properties of when it actually does this step or this series of steps. Let me move this out of the way so you can see the next option. So then again, update stats. We're going to do the same thing. We're going to update stats on the AdventureWorks database. Again, we can control which objects it's going to do it on. If we do just tables, we can select the tables that we want. We can tell it what types of statistics to update, and we can tell it how to do the statistics by doing a full scan, or we can sample certain objects. Now, way back in the beginning, we had an option to find a schedule. If we told it to allow each task to have its own schedule, we could specify a different schedule for each task here. We'll click Next. Then we can tell it what to do when the maintenance plan is complete. We can have it write a report to a text file. We can have it email a report. If we check the email, this option is not going to have anything in it because we haven't set up any operators for anybody to receive an emailed report for. So we click Finish on the summary screen, and we now have a database maintenance plan that is now going to allow us. Now, we didn't set a schedule for it, so it's pretty much what we refer to as an on-demand maintenance plan. So we would run it by clicking on it and saying run the maintenance plan now. In this demonstration, we got to see the process for creating a database maintenance plan using a database maintenance plan wizard. In this lab, you're going to perform the ongoing maintenance that's required in SQL databases. You're going to first start off by running DBCC CHECKDB to verify consistency and integrity in a database. You're then going to do a repair, allow data loss, and see the ramifications that that has on the data set. Then you're going to do a rebuild of indexes. You're first going to look at querying the database management views to identify fragmentation of indexes, and then you're going to implement a rebuild of an index. And then you're going to finish up by creating a database maintenance plan using the database maintenance plan wizard. This lab should take about 45 minutes.